All right. This is a demonstration on Bernoulli. The joke I tell is that guy blows. So these are just two empty old soda cans. They don't have a ton of mass to them. That's why they're ideal right now. I've just laid them next to each other. What I'm going to do is what Bernoulli did, and that's move some fluid. So if I get some air blowing between the two cans, what we're going to then make a prediction is, will those two cans play Beatles music? That means they come together. Or will they listen to Yoko, which means they will have been driven apart. All right, so I'm going to get some air moving towards you between those two cans, and we'll see what direction these two cans end up moving. You can tell they played Beatles music. They came together. Okay? All right? Reason being, right now, this can, let's just get her sitting still here, whatever, it's not moving. There are air molecules on all sides of the can. Those air molecules do not listen to my favorite band, One Direction. They don't. They listen to whatever band, I don't know, but they are moving in three X, Y, and Z shins. Okay, there's air molecules moving in an X, in a Y, and in a Z all around this can. The air molecules that are moving in the X shin pacifically that way are banging into the can. And since air is nice and evenly distributed in the room, there's a number of air molecules on this side of the can moving in the X's, about half of which are moving towards the can. So they're banging into the can this way, same number of air molecules banging in this way. There's no reason for this can to move. The net force due to the pressure times area is the same everywhere because the molecules are not listening to one direction. They're moving in X, Y, and Z randomly until I force them to listen to one direction. Now the air molecules on this side were moving towards you. They were listening to my favorite band, One Direction. They're moving in the Z, which means very few of them are available to bang into the can from the X, which means all of the molecules that were banging into the can on this way still are and are sufficient to push the can in the direction of the moving air current. All right, so please remember that moving air exerts less pressure than non-moving air, meaning a current. Okay, an air current. Air molecules are always dancing as long as they're above absolute zero, but they're moving randomly, which means pressure is evenly distributed in all their X, Y, and Z shins. But once I force them to move in, say, a Z, fewer of them are available to move in an X. So there are fewer molecules banging into the can on this side of it, more air molecules banging the can on that side of it. Therefore, push it towards the moving air. Moving air exerts less pressure. All right. Another example of that is going to be from this particular guy. This is a hair dryer, obviously. Anyway, what I'm going to do with this ping pong ball and the hair dryers, I'm going to get an air current coming out of the hair dryer. This ping pong ball is going to get stuck in that air current, and it will bounce up and down in the Y. That's fine. I don't really want you to worry about the motion in the Y. It's pretty easy to say why it's moving in the Y. What I want you to focus on is the motion in the X, or if you can tell the Z with depth in the camera, I don't know. But focus on the X. As this thing moves a little too far that way, something will magically push it back in. And as this thing moves a little too far that way, something will magically push it back in. All right, so pay attention to its wiggling in the X-axis, not so much the Y-axis. And what you could tell again is, like I said, is it was moving too far this way. All of the air coming out of this stream, out of the hair dryer, was too busy moving in the Y to bump into it in the X. So all of the air over here was bumping into it in the X to push it back into the stream. So it was always being pushed back into the stream of air because moving air exerts less fresh air. It is pushed, it is not pulled. Okay, please remember that. It is pushed, not pulled. Another example of this could be a little harder to see. I don't know. But can you tell this is the same piece of styrofoam? Well, it's a piece of styrofoam. It happens to be the same one I used the other day. What I'm going to try to do, it's sometimes it's hard to see from your perspective there, but I'm going to get an air current blowing on this side of this guy, and hopefully it will be sufficient enough. You'll see this thing move towards the air current. All right. Now, it's not going to be a huge amount, but it'll be hopefully noticeable. See, it's at an angle. You can tell it was being pushed towards the air current. All right, that's what I want you to remember. It's being pushed towards the air current because the air that was here was too busy moving that way. So the air on the other side was able to pull it. All right, this is another very common physics stration to demonstrate lift, where if I want to get that stretch of toilet paper to go horizontal just by making some air move, I could blow it from down there and it will physically push it upwards. That's easy. That's just a Newton's third law example. But what I want you to then focus on is what's going to happen if I get some air moving up above that item, and we'll see. All right, you can tell it went horizontal, didn't it? And that's because the air moving above the toilet paper roll was moving. The air below it was still air, so it exerted enough force to be able to lift that guy, so it went vertical. So there was a force that was able to lift something. I wonder what they would call a force that is able to lift something. I wonder what they would call that. I don't know. Perhaps we'll get in an airplane and find out someday. All right. What I'm going to do now is go over some of the math that is associated with Bernoulli. All right. So I'm going to get this guy moving. Hopefully the camera stays happy. A lot of times when I move the camera, it kind of craps out on me a little bit. But what I'm going to do is remind you about things that are in motion. Things that move have kinetic energy. All right. Kinetic energy is something you remember from last year. It is 1/2 mv for velocity. Now I'm going to use a cursive v for velocity squared. Okay. What I want you to remember about Bernoulli is we're going to talk about the kinetic energy of the moving air or any given fluid. That fluid of air coming out of the hair dry air is hard to measure its mass. So we're not going to measure its mass. We are going to substitute that out because the density, is equal to mass divided by volume. So a not cursive V is volume. A cursive V is velocity. All right? So if I rearrange this, that means mass is equal to density times volume. All right? Rho V is what I will use for M. So for fluids, okay, fluid kinetic energy. The kinetic energy due to the motion of a fluid is 1/2 rho, the density of the fluid, times V for volume of the fluid, times the other cursive V for velocity of the fluid squared. All right? That's the kinetic energy of a fluid, but we're not going to use it just like that yet. The other formula for energy I want you to remember is potential. You remember that from last year. That is mg, and last year they used an H. This year I'm going to replace an H with the letter Y for a position on a Y-sis, but sometimes I'm so used to using the letter H, I still use it. But please remember, H's and Y's are synonymous. They are the same thing. But I'd also like you to note that, gosh, this letter M looks strikingly similar to that letter M, which means I can replace it with mass, or rho times V. All right, so it's a rho times a V. So what I will do is say this potential energy formula. The potential energy in fluids is simply rho V, the density times the volume, times G, so mg, and then instead of an H, I'll try to remember to put a Y there for a position on a Y-sis. All right? Also, when things do exert a force, I want you to remember from last year, work. If you remember, work is what will give something potential energy or give something kinetic energy. Work is equal to a force times a distance. You guys remember that, right? Force times distance. What I'm going to do is I'm going to replace that letter D with just an L, a length, or a W, a width, or an H, a height. It doesn't matter, but a one dimension type of measurement. So it could be the same thing as a force times a length. Okay. Now, remember what I said earlier. Work is what gives things potential, gives things kinetic. If a system has work done on it, then that system will gain potential, or it will gain kinetic, or some combination of the two, right? If a system does work, if a system performs the work, then that system will lose potential or lose kinetic or some combination of the two. So please remember this from last year. Work is what will cause changes in energy. Please remember that. Work is what will cause, it will equal the change in energy in any given system. So here's what I want you to remember. Work, force times a length, all right? A force times a length will equal a change in. Change in anything is final minus initial. A change in energy. It will be, and I can go in kinetic first, kinetic energy final minus kinetic energy initial, plus the change in potential energy. Potential energy final minus potential energy initial, okay? Please remember that work equals changes in energy, the sum of the change in kinetic plus the change in potential, all right? This is called the work energy theorem. If that work takes energy away, it's a negative force times distance, like friction was last year. If that work gives energy to it, say I'm lifting a book, I give it kinetic and potential, okay? Please remember that. What I'm going to do now is rotate the page, because I'm going to put these versions of the fluids equation all together into one. So this force times length, all right? So this will be a force times length. That will equal kinetic energy final. The kinetic energy is 1/2 rho V, V squared. Okay. That's going to end up being kinetic energy final. 1/2 rho V F squared minus 1/2 rho VI squared. Okay? Hmm? Hmm? Then I'm going to push this plus button. Potential energy. Rho V G Y F minus rho G or V. Sorry, I wrote them in different order. Y I. Okay? Final minus initial. Rho VG. Okay? Force times length. Now, here's what I want you to realize that, again, that regular written V in print stands for volume. Volume appears in every term on the right side, but it does not appear on the left. But that's okay. What I'm going to do is divide everything by a volume. I'm going to divide that by a capital V. I'm going to divide this by a capital V. That by a V. That by a V. Now, I'm also going to divide this by a V. So I'm going to divide everything by a V. I'm going to do my least favorite thing in physics, and that is kill the V's. So what I'm left with on the right side of this equation is 1/2 rho velocity final squared minus 1/2 rho velocity initial squared plus rho G Y F minus rho G Y initial. Okay? Now, over here though, on the left-hand side, you see how I wrote a force times a length, and I divided that by a volume. Can you see how a volume is just a length times a width times a height? It's 3 dimensions. It's an LWH, or it's an area times a length. A volume is just 3 dimensions. So this could be written as force times length divided by length times area. A base times height times a length. 2 dimensions times that third dimension to give you volume. And that means those die, and I have force divided by area. That should mean, or should look strikingly identical to pressure. So pressure is what equals all of this. Force divided by area, which is pressure. Pressure is what will cause all of this. Okay? Please remember that. So pressure is equal to 1/2 rho velocity final squared minus 1/2 rho velocity initial squared plus the change in potential, the rho GYF minus rho GYI. Okay, so this is the work energy theorem. Please remember or realize it is the same thing as conservation of energy, or conservation of energy. You remember that from last year, right? That means the sum of the energy in any one location is the same as the sum of the energy in any two location, which means pressure, which is the equivalent to work, the fluid's version of work, plus 1/2 rho v squared, which is kinetic, plus rho gy, that's potential. The sum of the work, kinetic, and potential at any one spot is equal to the sum of the work, kinetic, plus potential at any other spot. All right? So what I'm going to call this is the pressure at any one location, plus the sum of now the, say, potential energy here. I'll just say pressure, and I could use force over area. It doesn't matter. I'll call it pressure, and then I'll say plus the rho Gy at any one location, pressure plus potential plus kinetic, 1/2 rho v1 squared, velocity. This is density, and then the v is velocity. At any one is the same thing as the pressure at any two location, plus the potential, rho Gy at any two location, plus the kinetic energy, 1/2 rho v for velocity at any two location squared. Okay, that whole big thing is Bernoulli. All right, that whole equation is Bernoulli's equation. It's the conservation of energy applied to fluids. Instead of work, we use pressure. And again, if you want, you can substitute out for force divided by area for pressure, force divided by area for pressure. I usually just leave it as a P, and that's the conservation of energy version of Bernoulli. All right. What I'm going to do now is the math. I'm going to use this equation, and I will do an example of the toilet paper with the hair dryer blowing. Okay. So I will use this for the toilet paper demo. Okay. So what I will do is start out with a diagram. Okay. This is the roll of toilet paper. That is what was the horizontal portion of the toilet paper. So the hair dryer was right there, blowing air that way. All right. Simple. So with that, what I want to ask you then is how many arrows in terms of this stretch of toilet paper to you see? And hopefully you see too, there is the force of gravity pulling that roll of toilet paper down. And there is that magical force that was able to lift that toilet paper up. And so literally we're just calling it the force of lift because, well, it's called the force of lift. All right. Those two arrows. This item is not moving. Once it gets in equilibrium and it's not falling down, it's not moving up, then the sum of the forces in the y equals may, which goes away. So the force of lift is equal to the force of gravity. All right. That should be very, very simple once I guide your thinking towards it, because this is what you guys did a whole lot of all last year, isn't it? Oh, Fg is equal to mg, isn't it? So the first thing I will do is I will get the mass of that stretch of toilet paper. This is that stretch of toilet paper. Okay, it's a Ballier. So what I will do, just put it on a scale, and you can't see the scale, but here, let me move it. Hopefully the camera stays nice. It's 0.47 grams. Okay, so I'm going to write that number down for the mass of the toilet paper, and I will put it in kgs. The mass of the toilet paper, 0.47 times 10 to the negative third kgs. All right. All right. Now, what I'm ready to do is set this up in terms of the Bernoulli equation, which is this: the pressure at 1 plus rho Gy, rho V, 1/2 rho V squared. This is Bernoulli's equation. I'm going to apply it to the toilet paper demo. Rather than using ones and twos, I'm going to use above and below. Okay? I will use above and below. So I'm going to simply rewrite this. I will say the pressure below the toilet paper plus the density of the air times the gravity of the planet we happen to be on times the y location below the toilet paper plus 1/2 times the density of air times the velocity of the air below the toilet paper squared is equal to this pressure, that potential, that kinetic. It's the same thing. I'm just swapping it out with B for below, and I will say pressure above, A for above, okay? Above and below. I like that better than ones and twos. That way you can keep track of where you're at. Is one above and two below, or is one below and two above? I don't know. It's easy to get confused. That's why I use a B for below, an A for above, and you should do the same thing. Rho G Y above and 1/2 rho velocity above squared. Okay? That should be pretty easy. Now, it looks like a very complex circaded formula. But what I want you to realize, I will move it again so you're looking at the toilet paper. Okay, I hope the camera stays nice. Sometimes when I move the camera, it stops working, but it looks like it's being nice. All right, good. When that toilet paper looks like this, all right, and it's somewhat horizontal, what I want you to realize is if I were to measure from the floor to just below the toilet paper, I'll get a number for a Y. But then if I were to measure from the floor to just above the toilet paper, I will get essentially the exact same Y. So the difference in Y from below and above the toilet paper is essentially zero. They're the exact same number. So what I want you to realize are the Y's will cancel. So the rho Gy, the contribution to potential energy in this example, goes away. There's very little difference in potential of air molecules above and below that stretch of toilet paper. Okay? Also, another one. Also, where would you expect the pressure to be greater? Below it or above it? Hopefully you remember when the hair dryer is blowing, the air is moving above it. Moving air exerts less pressure. So there'll be less pressure above, more pressure below, and that pressure is what is able to exert a force to lift it. So the pressure below we would expect to be greater than the pressure above. All right, that's why I put the PB on the left. Direct us toward the math that we're in the process of doing. The reason I went through that is so I could demonstrate to you the rho GY's dies. Okay. Also, the velocity of the air below the toilet paper. Remember, that is where the air is still, okay? Even though the molecules are dancing in all dir X, Y, and Z-tions, there's not an air current down there. The hair dryer was above the toilet paper. It was not below it. So the velocity of the air below the toilet paper will go away. We can call it zero in terms of an air current. All right? So what that means is the pressure below the toilet paper is the same as the pressure above the toilet paper plus 1/2 rho V, the velocity of the air squared above the toilet paper. All right? So I have to add these two numbers together to get the pressure below. Therefore, the pressure above has to be smaller by that quantity. All right? It has to be. And so what we'll end up doing is I will subtract this over. Okay? And what I'll have is the pressure below minus the pressure above. Well, that's a change in pressure, a delta P, isn't it? So I have a pressure below minus a pressure above. That's a change in pressure. That equals 1/2 times the density of the air times the velocity of the air above it squared. Okay? What we're going to end up solving for is the minimum velocity that is above the air in order to lift that toilet paper roll. Okay? Now, remember, pressure below minus above. The below pressure, now you remember what pressure is equal to? Force divided by area. So where that pressure below is going to be force below over area below minus force above over area above. Okay, so all I did was take pressure and replace it with force divided by area, above and below. That equals 1/2 rho velocity above squared. Okay, now the next thing I would like to remind you is to again show you this roll of toilet paper, this stretch of toilet paper that I was referencing. Do you have any idea what is the above and the below? You don't, do you? In fact, if I were to measure the area above and compare it to the area below, chances are I'll get the same area, won't I? So this area below and that area above are the same area, aren't they? Which means this fraction can be combined into one term because their denominators certainly do have something in common. There's so much in common that they are the same. So what I will do is say the force below minus the force above. This will turn into force below minus force above. So just the change in force over the area. That's it, because it doesn't matter if it's above or below. It's the same area. Is going to be the same thing as 1/2 times the density of the air times the velocity above squared. Okay? Now, here's what I'd like you to realize. The force above minus the force below. What this is the change in force. That is the lift force. The change in force below minus above. So this is air molecules. Now I'm going to draw air molecules. Okay, and I'm actually going to draw brown. I guess I could draw orange arrows. It doesn't matter. This force of lift here. All the air molecules are moving that way, aren't they? But over here, air molecules are moving up, aren't they? I mean, they're moving in all directions. Some are going that way, some are going that way. But for the most part, these molecules are moving up, these are moving that way. These difference in forces, those little arrows there, those difference in forces below minus above, there's a small number of arrows banging into it from above, air molecules. But that force below minus force above is what lift is made of. Okay, so even though force of lift is equal to mg, the force of lift is also equal to the difference in force below versus above. So I can say over here, the force of lift is equal to the difference in force. The force below minus the force above. That is what gives you lift. Below is greater than above. Therefore, I get a positive number. So the force below minus the force above is equal to lift. Lift is also equal to mg, isn't it? Okay, so FB, the force below minus the force above, is equal to mg. That difference in force is equal to mg. And look what I have there. Force below minus force above is equal to mg. All right? So mg over a, that's area. I'm going to solve for the velocity. What I'm going to find out is what is the minimum speed that air has to come out of that blow dryer in order to exert sufficient force to lift that item. So what I'm going to do is where this is, I will call it mg over a. That's going to be 1/2 rho velocity above squared. I'm going to solve for the velocity above. So what I'm going to do is multiply the 2 over, divide by the density, and then square root it. So this will become 2mg over area times density square rooted is the minimum velocity of the air above the toilet paper in order to get it to elevate itself. Okay? So 2 is easy. That is 2. The mass is what I measured at the beginning here. It is 0.47 E negative 3. That's kilograms. I'm going to multiply that by 9.8. That is in meters per second squared. Whoops, that's a 2. All right. Now I'm going to divide that by the area. I didn't measure the area. Sorry. This toilet paper there has a length of 28 centimeters. So I'm going to call it 0.28 meters. That's its length. Its width is right at 10-ish centimeters. So this will be times 0.1 meters. Okay. So there's the area. Now I got to multiply that by the density of air. This is 1.29. That's kilograms per cubic meter. All right. And I'm going to square root that. Now, when you do that, the calculator will give you a parenthesis. I recommend opening a second one, close it there, open and close 2. That's what I recommend you do as you type this whole entire thing all at once, which is what I will show you. Again, please do the math all at once. And you see how I did all the math with letters before I even put numbers in there? That's another skill you guys are already good at, aren't you? Because you did it all last year. So I will push the square root button first, and it gave me one parenthesis. I'm going to open a second one. 2 times 0.47, 2 times 0.47 E negative 3 times 9.8. I'm going to close one of those parentheses, and I'm going to now push the divide button. So you see there's my numerator. 2 times 0.47 negative 3 times 9.8. Close the 1. Now I got that divide button there. What I'm going to do is open another parenthesis, and I'm going to multiply my denominator, which is the area. 0.28 is the length. 0.28 times the width, which was 0.1. Going to multiply that by the density, 1.29. That's kilograms per cubic meter. That parenthesis closes this one. I need one more for the other one, and boom. The number will surprise you. It is not a very big number. It's about 0.5 meter per second. 0.51-ish meters per second, okay? It may be of interest for you to see where that number or where that unit comes from. Up here, I have a kilogram times a meter per second squared. That's the numerator. I'm going to divide it by a meter times a meter, which is a meter squared times a kilogram per cubic meter. Okay? Now, what this does is kill that. And what I can do now is flip and multiply this. So I will multiply it by a meter per kilogram. Okay? And you can tell that kg kills that kg. I'm left with meters squared per second squared, which is fine because We are square rooting it, so that's meters per second. Okay. Now, that's, again, a practice in what I call following the letters. So that is how you do Bernoulli, is able to lift a thing of toilet paper. Shoot, you guys all know we're in the middle of hurricane season because 2020 hasn't been a strange enough year yet. So we have, what, 2 hurricanes simultaneously right now. But roofs can get lifted off of buildings. Entire houses can be lifted out of their foundations. People oftentimes associate glass blowing inward, or it depends if there's something that flies into the window. But if there's just low pressure outside because wind is blowing, glass typically blows outward. Or you see in movies when a crack in, say, an airplane window or something breaks the cabin of an airplane, everything gets, they usually say, sucked out of the plane, but it is not being pulled, it is being pushed because the inside of the plane is pressurized to atmosphere. Since that plane's going several hundred miles an hour, that has the effect of meaning the air outside the plane is moving 400 miles an hour. That's a lot less pressure, so things get pushed outwards, okay? But Bernoulli, that guy blows. It's true for any given fluid. I've just given you examples with air, but when water flows, things get drawn towards that current. Anyway, this was a little longer than I would have guessed, 42 minutes, but hey, yay, physics.